Alright, so this video is going to be on infrared spectroscopy, an amazing tool to help us identify functional groups in organic molecules. So infrared spectroscopy, aka IR, uses electromagnetic radiation to identify the functional groups to give us something called an IR spectrum. And so here I've kind of posted a picture of the electromagnetic spectrum, and just more of as a refresher, right? So obviously this is our visible region. We have our Roy G. Biv, red, orange, yellow, green, blue, indigo, violet color framework there, and then we've also commonly seen that this visible spectrum is very, very small compared to the electromagnetic spectrum as a whole. But if you look just to the right of it, we have the infrared portion. And so that's what's used for IR spectroscopy, the infrared radiation. Just a couple reminders on some equations. The speed of light is equal to the wavelength lambda times the frequency of the light, nu, and then energy is equal to Planck's constant times the frequency of the light. Also, energy can be rearranged now to give you E equals hc over lambda, and from this information we can kind of see that as we go from left to right, we have an increase in the wavelength, and then as we go from right to left, we also have an increase in frequency. And in addition to this, we want to point out that as we go from right to left, we also have an increase in energy. Okay, so as we have an increase in frequency, we also have an increase in the energy. Okay, so how does IR work? Okay, so IR absorption basically causes molecules to vibrate, and this can be in the form of stretching or bending. So imagine two it's a common physics example as well, but you can also just think of two atoms that are bound together, and then as they kind of stretch apart from one another, that would be kind of the bond stretching. Whereas if we had, let's say, something like this, where we have a bunch of atoms bound together, and we can have the bonds bending together as well. And so I found a really cool app that I want to show you, and it helps visualize these things a lot better. And so we'll get to that shortly. But first, just a couple more things. When frequency of the IR is equal to the frequency of the bond stretching, that's when the IR is absorbed and a graph is produced, and that is the IR spectrum. Okay, it's important to note that bond stretches must lack symmetry, or they are what we call IR inactive. Okay, so bond stretches must lack symmetry, or they are IR inactive. Okay, so for example, carbon dioxide or an alkyne that's symmetrical. They do have IR stretches that show up in the IR. However, this kind of stretching modality that I kind of showed you before, where you have that basically the CO stretches going in opposition of one another, that is not going to show up in the IR, because you can think of it as almost canceling each other out. And the same thing is going to be for the alkyne as well. They cancel one another out, and so they're IR inactive. But as you can imagine, they can absorb the IR radiation and then bend, however, just like we showed above. And so when that happens, that does show up in the IR. All right, so a couple more things and then we'll get to the cool images. But if we're referring to frequency, oftentimes we'll refer to frequency in hertz. But if we were going to use that for infrared spectroscopy, we would have to report in this range, which is like kind of ridiculous, right? We're not trying to report values for like what does this particular functional group absorb in this range of numbers. It's crazy. And so what we actually do instead is we convert our frequency to wave numbers, and so this is denoted with what looks like the nu, but with a little wavy line over it, and this is equal to the 1 over the wavelength. And so the wave number is proportional to frequency, and so frequency is therefore increases as the wave number increases. And when we do this, we actually get to report our values from 4,000 to 400 inverse centimeters. So 1 centimeters to the -1, or 1 over centimeters, hence 1 over lambda, right, the wavelength. These are way easier, obviously, to report our numbers, and they make a little bit more sense. We can fathom the idea of these values much easier than we can maybe 1.2 times 10 to the 15. And so what we end up getting is a graph that, well, let me explain to you first, I guess. So every functional group is unique, and actually every bond technically is unique and absorbs at unique frequencies, right? Every functional group / bond is unique and absorbs at unique frequencies. And so that's why we can actually use this to identify functional groups, because a carbonyl is very, very different than a CO, like from an alcohol or an NH, or a CN. And so what we end up getting is again, the range between 4,000 to 400 inverse centimeters, but what we typically have is the functional groups range, or like the area of interest, is basically 1,500 and up, so greater than or equal to 1,500, while anything that's below 1,500, wait, did I get those mixed up? Yeah, I guess I should switch that. I don't like these darn greater than less than signs right now. They're making me angry. All right, so the functional group range would be greater than or equal to 1,500, while the anything that's less than 1,500 is something called the fingerprint range. Okay, and fingerprint range is basically an area in the IR that's really complex. It's not very instructive, and so we tend to ignore it. So, not usually instructive. And so we typically ignore it, and that's going to be the kind of like the main idea throughout the class, at least for this class. Once you get into more advanced chemistry, you might focus a little bit more on that fingerprint region, but I want to say that we'll focus mainly on frequencies or the wave numbers above 1,500, but it is helpful to take a look at some common like CO, CN, or CX bonds in the fingerprint region. All right, now before we dive deeper into this, I want to show you first what a kind of what we're looking at in terms of an IR spectrum, as well as what we mean by stretching and bending and wagging and things like that. And so I'm going to take you to a really cool app that I found. It's called WebMo. Sorry, let me actually close it so you can see what it looks like when it first pops up, WebMo. There's a free version to this, and there's also a $5 version where you can calculate things. So you can actually do theoretical calculations, which I think is really cool. Obviously, maybe slightly beyond the scope of the class, but you can draw out these molecules. As you can see, I just drew a carbon-carbon bond and then a carbon-oxygen bond. And what's really cool about this is, kind of look at it right now, I haven't drawn any hydrogens or anything. What I can do is press clean up on the top. I'm going to click comprehensive mechanics and check it out. It made my bond angles all happy, and it put the hydrogens in there. It even threw in the hydrogen on the oxygen. Now it looks like a cute little animal, little puppy, or the thing that drinks water. The little, like, I don't remember what they're called. There's some sort of energy mechanical thing, but there you go. That's an ethanol molecule, right? And what's really cool about this program is that you can manipulate it. You can rotate the molecule and kind of observe. Look, check that out. Boom, that's the staggered conformation of this guy. I'm not really sure how to draw a different, like the eclipse conformation of it yet, but I mean, with a little exploration, I'm pretty sure you can figure that out. But the cool thing about this now is that I can click the calculate button on the bottom, and then at the very top it says vibrations. And so when I do that, a bunch of things come up, right? So these are all, as you can see, inverse centimeters, and they range from 593 all the way up to 2926. And so these are going to be specific to ethanol, as they are going to be different for other molecules. But let's go ahead, let's click, like, I don't know, I like the 1114. So this is what we mean by vibrational modes, and looks like a happy little puppy, right? It's like, hey. But what's happening is this vibrational mode is absorbing the IR, and therefore we will kind of get that vibration to occur, and we get an IR spectrum. Okay, so take a look at that. I'm gonna go ahead and choose a different number now. Let's go back up. Let's go up to like 2900. You can see a different portion of the molecule is wagging or bending or vibrating a little bit more. Let's choose another one. And so that's a different portion of the molecule. And so this is what we mean by bonds stretching or bending. And this only occurs when those particular frequencies of those stretching or bending are the same value as the incident IR radiation that you're applying to it. And so when they are equal, you get this, and you get an IR absorption. Okay, now let's take a look at what this would look like on paper, right, in an IR spectrum. So I'm going to take you to another really useful website now, which is the Spectral Database for Organic Compounds, SDBS. Go ahead and type that into your web browser. It'll pop up real quick. You'll get this screen. You agree to the bottom disclaimer so that you can look at all of the cool IR spectra, or just spectra in general. Ethanol is what I'm going to type in the compound name. You can type in other things as well, but obviously tons of things come up. But we can go ahead and find ethanol. Let's just zoom into it, right? Ethyl alcohol is the one we're going to choose. Now on the top, you can see there's MS, that's mass spec, CNMR, that's carbon NMR, HNMR, that's proton NMR, IR is what we are learning about right now. And so we want to go ahead and click on that, and we will get an IR spectrum for ethanol. What? Check it out. Check it out. Whoa, whoa, whoa. Simmer down. Okay. I don't know what's going on, folks. All right. So this is an IR spectrum. As you can see, the x-axis is ranging from 4,000 all the way to 500, 400. And then on the y-axis, we actually have something called transmittance, and this is basically the light that makes its way through to the detector. So 100% transmittance means all of the light went through and none was absorbed, meaning none was absorbed to make the molecule vibrate. And so anything that kind of dips down, that's where the infrared frequency matched the frequency of the bond bending or stretching, and so it was absorbed, and that's why we don't get any transmittance at that point. Now this is what we use as a useful tool, because as you can see, at least for ethanol, there's not much above 1500, which is why we focus on that region. And we have some stretches at around 3000. There's a little tiny cluster. Now those typically correspond to CHs, and then we have that really broad one, right? Looks kind of like I don't know, it's melting. It looks pretty cool though. And that's very characteristic of an OH and an alcohol, okay? And so this is essentially what we would be looking at to help us identify what our compound is or what our functional groups are, okay? And so that brings us back to a few other things I wanted to say. So I will make note of it again. So the x-axis is wave numbers, and that ranges from 4,000 to 400 inverse centimeters. And then we also have the y-axis, which is equal to percent transmittance. And that's basically how much light makes it through, how much light makes it through. All right, and so we do have some pretty common regions for specific bonds, and so what I mean by that is, let me draw a little chart for you. Let's see, we got, boom. So an OH, an NH, and a CH. So we're looking at these bonds to hydrogen. Now we've got, here, I'm gonna try and make this try not to make it ugly. We've also got a triple bond to a carbon, and then a triple bond with a nitrogen. Okay, we've got a carbon-carbon double bond, a carbon-oxygen double bond, and a carbon-nitrogen double bond. And then we've got CC, we've got CO, CN, CX. Okay. Now, as we go from left to right, we have an increase in inverse centimeters or wave numbers, and we also have an increase in energy, right? So increase in inverse centimeters, increase in energy. Okay, now we can also focus a little bit more closely on what we're actually looking at, right? Notice the CHs are all over here. Boom, boom, boom. I'm sorry, the hydrogen bonds, like the OH, NH, and CH. So these are all bonds to hydrogen, right? And these, the next column right here is the triple bonds. And then we have the double bonds. And then we have the single bonds. what you might remember from physics, Hooke's law. So Hooke's law. And so let's say we're looking at a spring. A stronger spring vibrates at a higher frequency, right? And also springs with lighter weights vibrate at a higher frequency as well. And so what we get is K. K is a constant times the square root of F over M, where F is the force constant and M is the mass. And so if we have something with a small mass, like hydrogen, right, then we get a higher frequency. Okay, and if we have something with a stronger bond, then we get, so strong bond equals higher frequency as well. And so that would be like a triple bond. Triple bonds are stronger than double bonds, which are stronger than single bonds. And so that's why we have those at the in the following order, right? And so this is basically just to help you understand why these things are located where they are and their relationship to or with IR frequency absorption. So bond strengths, bond lengths, size of the atoms, etc. Now that would be, this is more of a general chart right here on the top, but then now we have very common charts. So this is for important IR absorptions, just very general, right? And then we also have this one, which is more specific to the various functional groups. So you can see that this region is broken down more specifically, not just general carbonyl groups, but esters, amides, aldehydes, etc. Okay, so let's go back up to this one real quick. These are both something that you're going to want to commit to memory and kind of understand why and where these are showing up. Because if you look at an IR, you should automatically know what functional group is in that molecule that you're absorbing or that you're observing. Now let's focus specifically on this region right here. As you can see, we have the CSP3, sp2, spCHs, and you can see that the range, although they do overlap a little bit, you can clearly see that this is lower wave numbers and this is the higher wave numbers, right? And so this is because of the difference in S character, right? We have 25% S, we have 33% S, and then 50% S. And remember, the strengths of those bonds are going to vary, where we're going to have stronger CH bonds between the CSPH. So CSPH is the stronger bond because of more S character. Okay, and so that's just the general trend. If you have increasing percent S, you're going to have an increase in inverse centimeters or frequency absorbed. So as you, increased S character equals increase wave numbers. Okay, now that is one kind of, so all of the other ones are kind of generic, right? Either bond strengths between different atoms, that's obvious, or total number of bonds, like a triple bond is stronger than a double bond, obviously. But we can also have an effect with on the absorption of the IR with ring size as well as resonance. And so how would resonance affect the absorption? Let's do that one first. and then we can get into the ring size, resonance. Okay. Now, before we start talking about resonance, notice that in this chart up here we have a bunch of carbonyl groups, but they're incorporated into different functional groups like esters and aldehydes and ketones, for example. And they range from maybe as low as 1630 to as high as 1745, right? And so why is that so drastic? And we can look at the resonance structures of these things and see pretty much how that plays a role. And so the first one I want to do is actually something called an alpha beta unsaturated carbonyl group. So it's going to look like this: alpha beta unsaturated carbonyl. Okay, and that's because this is the alpha position, this is the beta position, and it's unsaturated because it's an alkene. It doesn't have all the hydrogens on it. Now, if we were to draw a resonance structure, let's say we just kind of did this, right? Now what do we get? Well, we get something that looks like this. And so this is still the alpha position and the beta position. And since we get some degree of this guy right here, what that means is that we actually get some, or let me write this in red because this is the key thing, some CO single bond character. Okay, and what I mean by that is, remember, resonance structures kind of, I didn't draw the positive carbon over here. Resonance structures kind of represent what the molecule looks like, and they're just snapshots of it. So there's going to be some degree of this guy and some degree of this guy at different proportions depending on how what the preferred location of those electrons is. Obviously the one on the right has charges, but nevertheless it still can have some contribution to the resonance structure and overall the structure of the alpha beta unsaturated carbonyl. And so what that means is, since we have some single bond character, remember the trend in general is a CO double bond is stronger than a CO single bond. But if we have something that's somewhere in between, then that's going to shift the IR absorption to the right. Okay, that means another way of saying that is the CO bond is weaker, so weaker bonds absorb at lower at lower frequencies or at lower wave numbers. Weaker bonds absorb lower wave numbers. And this is a very common thing that we're going to see. Now this can actually translate to a variety of compounds. So, or I guess it can, I don't know the word I'm looking for, but it can look quite different depending on the overall structure of that particular either alpha beta unsaturated ketone or something else that can be kind of really heavy on the resonance structures. So for example, let's take a look at this guy versus this guy. So this is an alpha beta unsaturated ketone on the right, and what we've got is 1685 for the wave numbers for this guy and 1715 for this, because we can have that resonance but we can't have it over here, and so we've got a shift to the right or to lower wave numbers. In addition to that, a really interesting one is, let's say we're comparing this guy to this guy. Notice the benzene ring there as opposed to just having one pi bond in there. So this 2 is at 1685. And this one, however, is at 1709. And so it is a common thing that if you have a benzene ring that is pretty much adjacent to a carbonyl group that can therefore undergo resonance, then we get a lowering or a decrease the wave numbers by approximately, let's erase that, lower the wave numbers by approximately 30, okay? And that's just kind of something that we see that's very typical, and so keep that in mind when you're looking at the absorptions. Now, another thing to add about these types of compounds, the carbonyl groups, is that they can actually vary from atom to atom. And so let's take a look at an ester versus an amide, for example. It's all about the willingness to create that resonance structure as well. So just because you have a carbonyl group with next to an atom that has a lone pair doesn't mean that it's always equally willing to create that resonance structure. Okay, so what I mean by that is, yeah, we can kind of donate these electrons to create that resonance structure, or these electrons to create that resonance structure, but ultimately, which one is more willing? And nitrogen, as you know, is more basic than oxygen. It's also considered, therefore, a good pi donor. So meaning that it's going to donate those electrons to create a pi bond. And so if this is the case, then that means we're going to have a lower wave numbers for the amide than we will for the ester in this case. So oxygen is less basic, less willing to donate electrons, and so this is going to have higher wave numbers. Sorry, let me be explicit again. The reason why this is lower is because you have a greater population of this resonance structure in the end. Okay, and so this is going to be a very good contributor, not necessarily maybe the main contributor even, but that nitrogen is such a good pi donor that you have a greater population of that resonance structure than you do this resonance structure. And so that's why we're going to have greater CO single bond character in the amide. And so let me draw the population, and that's going to be greater CO single bond character, and therefore the lower wave numbers. Okay. Now, another thing we want to take a look at is the ring strain, right? And so when we're looking at ring strain, we want to take a look at basically the size of the ring and see the trend. So here's a cyclohexane, it's cyclohexanone, this is cyclopentanone, and this is cyclobutanone. And as we go from left to right, you can see that there is an increased ring strain. Okay, Okay, and along with that increased ring strain, we get an increase in the wave numbers. And so this one's actually 17, sorry, this is 1715. It's actually pretty typical for a ketone in general, that even for like the straight chain ones. And then 1745 for this guy, and then we've got 1780 for this guy. And that is the general trend. Increased ring strain equals increase in wave numbers, and this is due to the decrease in bond angles of that ring. Alright, so let's take a look at what the heck this translates to in terms of what these things are going to look like on a mass spectrum. So first things first, let's take a look at just a typical CH containing compound, a hydrocarbon, hexane. Really, all we're looking at is, remember, this is the beginning of the fingerprint region, so we're going to kind of ignore everything to the right of that, and so that leaves us with only the CsP3H's, and that is the most telling, that pretty much all we have is carbons and hydrogens. And notice the look of it. So the look of that pretty much indicates that we only have CsP3 hydrogens, as opposed to hexyne, which is the same number of carbons, but we actually have an alkene in there. Now, remember, this is the double bond. This is the fingerprint region from this here to the right, and so we do have something here now, and that is the CC double bond. It's not super strong or obvious, but it is there. And then we have these CsP3 hydrogens, again, CsP3H's, and then we have this little nubbin right here. I like to think of it, it's almost like you can think of this like a weird creepy hand sticking down. It's pretty much like the dew claw for a little puppy, right? It's kind of like way back there, but it looks like a thumb of a hand, but it's like way too far back and weird to be a human maybe. And so that's what the CsP2H stretch shows up and looks like. And let's take a look at the alkyne. So it is hexyne, just to kind of compare and show you how much the IR does change. Again, we are kind of looking at this from here. We're ignoring from the 1500 over. Now this CC triple bond, notice it actually moved a little bit higher in wave numbers compared to the CC double bonds, as expected for an increase in that strength of that carbon-carbon bond. We pretty much still have the CsP3H's there, and then in addition to that, we also have a really strong absorption for CsPH. Now it's also a little bit further increase in the wave numbers compared to the CsP2H, right? And so this is again because of the increased S character of that carbon, and therefore a stronger CH bond. All right, let's take a look at an alcohol functional group now. Pretty much get to ignore this region again from here over. You can see over here is a little bit more complicated now because we do have like a CO stretch in there as well as an, and so what we do have, which is very obvious, is the CsP3H's, and then this super broad one right here, right? This is indicative of an OH. Now notice the range, general range is right here to right here perhaps, because carboxylic acids are a little bit more broad. All right, so here's the example of the carboxylic acid. As you can see, the range is much more drastic. So this kind of died out around 3600. This goes even maybe a little bit further over here, and then definitely over to this range as well. It's around 2500. And so that's characteristic of a carboxylic acid. If you have that, notice the CHs are kind of hidden. They're not as obvious anymore like they are in the alcohol, if you have that occurring. As well as the CO double bond right here at 1700-ish. then you're automatically thinking the carboxylic acid functional group. Okay. Now looking at butane 2-one or 2-butanone, this also has the characteristic CO stretch, C double bond O stretch, as well as the CsP3H's, and that's pretty much it, as everything else occurs to the right of the 1500 mark. Okay. Now we have a diethyl ether. So this is an ether functional group. It does contain an oxygen, but notice there's really not much going on. Most of the stuff is to the right, but we do have the CsP3H's, and that's about it. So if we know we have an oxygen, but we don't really see a carbonyl or an OH, then we're thinking it's an ether. So let's take a look at the amine. We have, again, let's see, we're kind of really cutting it close here, right? The main thing we want to focus on, especially with a primary amine, is the presence of the NH's. If we have two little blips to the left of the CsP3H's, then we are kind of going to think amine. If there's only one, then that means it could be a secondary amine. So one NH stretch, that could be a secondary amine. Okay, now let's take a look at an amide. We got that CO stretch in there. That's pretty indicative of a carbonyl group. But then now we also have a very large NH stretch, and that's going to tell you that you have the amide. Here's the nitrile group. That's a C triple bond N. Again, we're really just kind of focusing on everything over here in the functional group region. We got the CsP3H's, and then the CN triple bond is right there. Now notice the CN triple bond is really close. Let's see, what do you want to call that? That's about 2250. And then the alkyne is also around 2250, right? I bent that a little bit. It's a little bit to the right, but they are really close. But notice the if it's a terminal alkyne, you're going to have this CsPH, and that's really obvious. And so that's one way you can differentiate between that as well as a nitrile group. In addition to that, this nitrile group would have an odd mass because of the presence of that nitrogen. So if you had that option to kind of observe what the mass spec was, then that would be a way to identify or differentiate between the nitrile as well as an alkyne. Now, that's kind of the common methodology, and that's using mass spec as well as IR together to determine the unknown structure. All right, y'all. What you think it's time for practice? You want to talk about practice? Let's do one of the combination problems of IR and mass spec, because that's what you really want to do. Hydrocarbon X has an M plus at 82, so the molecular ion has a M over Z of 82, and the IR of X has a peaks at 3300 to 2850, 2250, as well as, and then also propose a structure for X. So pretty much what you want to do is focus on the mass spec first, and then go to the IR after. So we are not given anything other than the fact that it's a hydrocarbon. And so what we want to do is apply the rule of 13. So we're doing mass spec first. Rule of 13, you divide that, you get about 6.3. Okay, so remember, we can't have a 0.3 of this represents a CH unit, and so that means we would have C6H6, and then 0.3 of a unit of CH, which we can't have, right? So if you convert, basically this 6 times 13 equals 78. And so that means we have a remainder of 4 units to get us to 82. And so that means we can basically add 4 hydrogens. Okay, and that goes to C6H10 for our proposed original structure. Okay, so what we want to do now is calculate the degrees of unsaturation. And so the way we do that is first decide what the saturated hydrocarbon would have. Saturated equals C6H14. Okay, so now since we had the saturated would have 14, but we actually have only 10, we have to find the difference between the two. So 14 minus 10 divided by 2. And that is going to give us 2 degrees of unsaturation. Okay, and so what that means is we can either have 2 rings, 2 pi bonds, or a combination of 1 ring and 1 pi bond. Okay. Now, what we want to do is think about what functional groups are in this, and that's going to be, we're being told what that is based off of these stretches over here. So at first, you're going to have to refer to the chart quite a bit, but that's why you got to practice, because then eventually you won't have to look anymore. So let's look at the, let's look at all of them, right? So 3300, let's look at that first. So if we look at the chart above, we have something at 3300 right here. Now you do have some other stuff that's around 3300, but the question was very specific. It said 3300, and that was it. There wasn't a range like for this guy or this guy. And it is a hydrocarbon, so it's very possible that we can have an alkyne. So we'll have a CSPH. So let's go back down now. That means if we have a CSPH, that means we have to have at least that portion of the molecule in it. And this would be contributed, or this would contribute to the 3300 inverse centimeters. Let's look at the 3000 now to 2850. This is pretty straightforward. I think you'll see that a lot. So 3000 to 2850 is at the top, and that is your CSP3Hs. So that portion right there, if you just went ahead and you have a bunch of CHs, that's going to be your 3000 to 2850. Okay, now your last one is 2250. So let's see what that 2250 could be. So it's not here. Ooh, check that out. Oh, well, that's expected, right? Because we had that CSPH. And so there you go. That is pretty much all of the, we wanted 2250. That's pretty much all of the stretches that we were trying to figure out, or that we're using in order to figure out what the structure of a molecule is. And so a proposed molecular structure could be, let's piece them all together. So that's 1, 2 carbons. That actually takes care of the alkyne with the CH, as well as the alkyne triple bond that we have at 2250. Now all we need is a bunch of CHs, and so we have I'll just put CH2, that's 4 carbons. So we need 6 total, 5, 6 with the 3 hydrogens. And so this is a hexyne. And so if we look at hexyne, I actually had that example here for you. Let me erase all this garbage. We have that, what that peak is at 3300. We have the 30,000 to 2850, and then we also have that 2250 here. And so that's pretty much what they're saying. okay? And that's the process that you want to take in order to identify what or unknown compound you have. Now, that's not the only type of question that you can get. So what you can also get is, um, let's say you had this particular formula and it was treated with zinc and mercury as well as HCl, and then you end up with some unknown compound Z. Okay, the molecular ion of this is 92, and we have some absorptions of 3150 to 2950, 1605, as well as 1496 inverse centimeters. So what is a possible structure of compound Z? Now, so this is benzaldehyde, and we would be given that, and so we need to know that the structure of benzaldehyde is this. Okay, we don't necessarily need to know what the zinc mercury amalgam with HCl does. Obviously, when we get more advanced in organic chemistry, we'll know that, and so this problem would be very easy. But since we don't know that, what we want to do is kind of figure out what the possible structure would be of compound Z, starting again with mass spec. So 92 divided by 13, applying that rule of 13, gives 7.07, so that's pretty much C7H7 with a remainder of, let's see, 7 times 13 is 91 with a remainder of 1, so let's go ahead and add that extra hydrogen. Here, let me not just do, so plus 1 hydrogen to get 92 for the mass, and that equals C7H8. Notice this compound over here, there's 6 in that benzene ring, there's 1 in the carbonyl, that's already got 7. And then it's got 1, 2, 3, 4, 5, 6. And then there was an oxygen, right? Now our formula has changed to C7H8. So what's a possible structure for that? Well, let's take a look. What is the degrees of unsaturation? So du is equal to, so what we want to look at is the saturated compound first. So C7H16 is what that would be. And, sorry, since we have only 8, we do 16 minus 8, which is 8 divided by 2 equals 4 degrees of unsaturation. And remember, when I said if there's a high number of degrees of unsaturation, we're usually going to think that there's a benzene ring in there, which there was to begin with. And so it's very likely that nothing happened to that benzene ring, especially since benzene rings are not super reactive. But so if that's the case, we have 4 degrees of unsaturation, and what we also need is to look at the IR structure, or the IR spectrum, right? So 3150 to 2950. Now that, let's take a look at our chart up here. That could be, what was the number? I don't even remember what the number is. 3150 to 2950. Okay, so 3150 to 2950. So that could be something like this, and it's also kind of bordering that alkane line, but either way, we have some CHs is what we're looking at. Now the rest of that was 1605 and 1496. So let's see if that's in this chart. Yeah. So right here we have benzene shows up at 1600 as well as 1500. So we had 1600 and 1496, which is benzene. Okay, so what that means is we probably just have a benzene ring, which is 6 carbons let's throw another carbon on there, and then that's it. So we've got 1, 2, 3, 4, 5 hydrogens on the ring. We have a substituent on it, which is a methyl. So there's 5 plus 3 is 8. So that's C7H8. And this would be our proposed structure for that particular problem. All right, so again, this is going to take some practice. So take a look at the chart as well as the spectra that I have kind of shown you. There's plenty in your book that you can refer to. And then you can also use that spectral database to kind of search molecules on your own to just kind of take in more spectra. So that way when you see something, you'll just automatically recognize it and you'll know exactly what it is. And if you have any other questions, please let me know. This stuff is really fun. You just gotta kind of go in with a positive mindset and just kind of enjoy the process, because it is a process.